And we are back with P-Set 7 solutions. Actually, let me change my marker. Let's get our good old red friend back. So that's looking good. All right, let's go ahead and get started. So we have this dynamic mechanical testing that's done on the material. So remember, we have G prime is our elastic response storage modulus. G double prime is our loss modulus. So it's our viscous response. So material here. So dynamic testing is on the material as well. The beam material is the black curve. Label the x-axis in terms of temperature and give some relative values on the x-axis. Do the same for time, rate, frequency, what material is the most solid, what's the most viscous, etc. So it gives you it gives you this, so it's actually should be quite easy. So if we're looking for temperature, so we know at high temperatures what response should dominate. So at high temperatures we should be viscous. So our G double prime should be dominating. So that's this side. So for all these materials, so this should be like 100, K, and this could be like 0 K. So that would be for temperature. Temperature scales similarly with time, right? So at very, very, very short times, so at like 0.1 seconds and 100 seconds, at very, very long times, I'm going to have my viscous response. Frequency, on the other hand, if I have a frequency axis, that's flipped. So at very, very, basically, at very, very, so at, actually, let's see, G double prime here, exactly. So here, this would be long time, and then very, very short time will be my elastic response. High frequencies, so 100 here, and very low frequencies here. So high frequencies will give my elastic response, and then low frequencies will give my viscous response. So which material is the most solid, most viscous? So if I'm looking at, for example, my relaxation frequency here, no, you do have my mouse. Excuse that. So I always like to think about relaxation frequency. So if I look at my relaxation frequency here, actually we can just do it in terms of TG2, but we can kind of look at both. So this is my crossover point here, here's my crossover point here, and here's my crossover point here. So if I look at relaxation frequencies, so my relaxation frequency here is the lowest relaxation frequency. So what does that mean? So if I have a very, very low relaxation frequency, so that means if my F relax is very low, that means my relaxation time, tau, is going to be very, very large, high. So what does that mean physically? Well, it means that if I have a large relaxation frequency, or relaxation time, excuse me, if I have a very large relaxation time, it's hard for that polymer to readjust and basically reconfigure. So that polymer is going to behave very, very elastically. And actually we can kind of see that there on the temperature range too, because this crossover point can similarly be indicated like a TG, right? So this has the highest TG, second highest here. So this is going to be my most elastic, then this, and then this. So there we go. We got it. Fill out the regions of the deformation mechanism maps. Rank the yield strength and grain size for all curves. So we know this is theoretical, 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 dislocation glide, dislocation glide, dislocation glide, dislocation glide. We know the top power law creep, PLC, 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 PLC. What else do we have here? Elastic, elastic, elastic. We know the rightmost is Nabarro-Herring, Nabarro-Herring, and Nabarro-Herring here. And then this is Coble, and then this is Coble, and then this little guy is Coble. All right, so what do we have here? So again, we filled it out. Let's rank for A, B, and C. Actually, it says here, actually for all of the curves. So I see that this seems to have actually the highest yield strength. So my yield strength of D is greater than, probably the next one would be yield strength of C, which is greater than, those are pretty close. Here and here. It's very, very similar. So let's say we're equal to them. But we know that definitely B is the lowest. All right, that's definitely the highest. These are pretty close. Hard to see there. But just make a suggestion. A or C can be, actually I think, looking at it, I think this should be, it's hard to, I think C is, I think that ranking is correct. All right, what about the grain size? This is a little trickier because if I look at cobalt here and cobalt here, they look to be the same grain size, but I know for A, B, and C that basically my dg of B is greater than dg of A, which is greater than dg of C. And we can see that from the ranking of our, we could actually easily see that. Yeah, it must be C and A. We can see that from our ranking of our yield strength as well, if we're grain size strengthening. But to me, I think that basically C and approximately dg of C, dg of D as well. So those look to be pretty similar to me, based on the cobalt creep region. All right, draw the stress strain curves for A, B, and C. What are probable strengthening mechanisms? What are the scaling behaviors? So I'm seeing A, B, C. It seems like that the cobalt creep region is changing, so it must be an annealing process. So that means that my change in yield strength scales with to the 1/2, or cold working or annealing, or it could be alternatively my yield strength changes as grain size strengthening, dg to the -1. But these appear to be the same material. So for example, we'll have, this will be, and then B, this will be same Young's modulus, this will be A, and then this will be, again, poor drawing, but C. Excellent. What about C and D? So C and D, it doesn't look like it's grain size strengthening or it's cold working, but there is that big shift. So it could be, I could have solute strengthening, so the 1/2, or I could have precipitate, cutting and bowing. Either way, my stress strain curve will look like, so that could have a slight change in the Young's moduli. So, but it could be like this, or it could be like this. So this could be, for example, C, D. So again, that's fairly, actually not fairly, it's very exaggerated, but yeah, that's that's very exaggerated, but again, it's just an example of what could possibly be that that solution. Most likely, even if you alloy your material, it's just going to have a very slight change here, but it will have a different Young's modulus. All right, working with, okay, we're all back to our old friend, our polymer. So let's remember, how do we solve this problem? Actually, let's read this problem. So we have our stent problem that we had previously, and what will be the critical crack size to fail in the stress state? Note that the surface tension is 100 joules per meter squared. So we have a couple, oops, my pen just fell. We have a couple of failure fracture equations, effectively, available to us. What are they? Well, one of them is our Griffith criteria. So we know that our stress at failure equals square root 2 gamma E over pi A critical. We also have stress at failure equals square root of G E over pi A. So this is our Griffith, this is our Orawan, and then we also have stress at failure equals, actually K1C square root pi, actually, excuse me, that's K1C equals, I think, a factor, but we can just do square root pi A. That is correct. Pi C. And there's like a prefactor there. But anyways, the point I'm trying to make here is this is a polymer. So Griffith criteria, that only works for ceramics. So that's not going to work. We're not given K1C here, so we can't use that equation. This is the equation that could work for, only this one and this equation can work for polymers. But since we're not given that information, we actually cannot solve this problem. So that's actually the point, is making sure that you're using the correct criteria, for the correct failure mechanism. And that is PSET 7. That's it. So we will see you all in the next video, and good luck on the exam.